Hello everyone, welcome to another physical sciences lesson, and our topic is all about electrochemistry. And we're going to be doing something rather special today. We're focusing on the table of standard reduction potentials. So let's go and have a look and see how this all fits together. So my first question to you that follows on from our previous lesson is the zinc copper cell the only galvanic cell that we're going to be looking at? It's quite an interesting question, and in fact we're going to answer it by looking at a series of information that we can get put together, which we call the table of standard reduction potentials. Let's see how this all fits in. So you'll remember that in electric chemistry we've got the galvanic cell, which we've spent some time on. We focused on the fact that it has an anode and a cathode. The anode is where oxidation takes place, and the cathode is where reduction takes place, because we look for the red cat and we look for an ox. They are joined by a salt bridge, and we know that we can draw diagrams of these, or we can simply put them into cell notation, where we have a specific order of putting those components. So we can show the electrode, what's in the solution, the salt bridge, what's in the solution, and the following electrode. We're going to practice a bit of that as well a little later. But what our focus today is on the redox reactions, and in particular the standard reduction potentials. We're going to be talking about this mystery, which I've put down as She. Now, She is really the standard hydrogen electrode, and we'll have some reasons to share about exactly what that's about. So let's move on and jump straight into our discussion today, and by referring again to what we've done previously, where we took some zinc and we placed it into a solution of copper, a copper solution. I think this was copper sulfate. After a little while, we took out the zinc and we found there was copper at the bottom there, and there was copper deposited on that as well. So the equation that we got was copper went into copper sulfate, zinc went into copper sulfate, and that produced zinc sulfate, and copper was the deposit. We recognized we could break that reaction into two half reactions, where we'd say zinc loses 2 electrons, those are the electrons there, to form zinc ions. This is therefore called an oxidation reaction. This is an example of direct transfer, where they're in contact with each other, where the copper solution has copper ions to start with, and it gains those electrons to form the copper metal. This is reduction. Please remember as well that this substance that undergoes oxidation is called the reducing agent. So the zinc here is the reducing agent, and it has donated its electrons. The copper ions here, copper ions, are the oxidizing agent because they've taken electrons. So this balance between oxidation, reduction, reducing agent, oxidizing agent, something you must be very familiar with, both for direct transfer, but also for what's happening in the galvanic cell. So we recognize the same sort of thing is happening here. It's the same sort of reaction where zinc at the anode is undergoing oxidation. So the zinc electrode here is the reducing agent, where in the other half cell, the copper ions are the oxidizing agent. And we're recognizing that's the reaction for there. It's undergoing reduction. That's the cathode, that's the anode. And remember that because this is the reducing agent, it's donating electrons. So electrons are going to move through the external circuit from the zinc electrode through the voltmeter, and it's going to end up on the copper electrode. anything that's a source of electrons is going to be a negative terminal, and anything that's accepting electrons is going to be a positive terminal. So the zinc electrode is considered negative, and the copper electrode is considered positive. Flow, or the movement of electrons from the zinc through to the copper, as I've indicated. And that gives us a reading on the voltmeter. And in this case, I want you to notice that this is a positive reading, telling us that this reaction is a spontaneous reaction. It happens without any energy because this is a galvanic cell. It's one in which we're finding electrical potential is converted into, chemical potential is converted into electrical potential energy. And it's the difference between the ability of these half cells to react or have a reduction potential is the reason why, when we connect them together, we've got this reading on the voltmeter. So let's explore that in a little bit more detail. And when we asked the question earlier about, is the copper-zinc cell, the zinc-copper cell, the only one? Well, no, it's not, because we recognize that chemists have a way of comparing reactivity, what they call a reactivity series. And one other example of this is if we take copper wire and we place it into a solution of silver nitrate, there's another direct transfer of electrons. So it's direct transfer of electrons. It's an example of a redox reaction. But this time, the copper is the one that is going from copper to copper ions, plus 2 electrons. And this solution, that white stuff that you're seeing there, is actually the evidence of another reaction taking place. And I'm just going to change the color of my pen so you can see. What's happening there is the silver ions in the solution are gaining electrons to form that white substance that we see there, which is actually silver. So that's the silver that's forming there. So we can recognize there are a whole lot of these displacement reactions taking place, and that means that we should be able to get a whole lot of different electrochemical cells, which we know in this case, an example are also called galvanic cells, because they're producing electricity for us. As I said, these are displacement reactions, and by doing a whole lot of displacement reactions, we can get a series from the more reactive. These ones are more reactive, and these are less reactive. And you can do this by a number of ways. In the end, having a series like this, I want you to notice these are metals, group 1 metals here, and these are the transition metals. These are relatively unreactive, and in the middle is hydrogen. Now, here's our table of standard reduction potentials. Where it comes from, I'm going to explain a little later, but what I want you to see is it gives us an order of things in their ability to be reducing agents. So on this table, we see these are the strong reducing agents. And on the next slide, we'd recognize that this down here, fluorine, is the strongest oxidizing agent. Okay, and so as a consequence, let's just look at what the information this table is doing. We're going to zoom in on that reaction there, and we recognize the reaction with zinc. I want you to see that zinc going to zinc ions is the oxidation reaction. Whereas, if we could take the reverse reaction, in that case, this is the reduction reaction. So zinc can undergo both oxidation and reaction and reduction, but it actually prefers undergoing, if you start with zinc as a metal, it prefers undergoing oxidation. So zinc is a reducing agent. Now, in comparison to others, it's a fairly good reducing agent. But how do we know? How can we test it? Well, of course, the thing that chemists do is they do investigations and they compare reactions. And so I want to take you through the idea of comparing a zinc half cell to other half cells. But I think it's time for a short break. When we be back, we're going to investigate She in more detail. So see you after the break.